All right, so this mini lecture is going to look at kind of the conceptual or ray tracing way of getting an image with a thin lens, a convex lens specifically. So I have drawn up on the board, here's our representation of that midpoint of that convex lens. Here's the optical axis, and I've identified both of these focal points. So this is the near focal point, and of course here's our far focal point. We're going to assume this lens is symmetric, so that tells us that the near and far focal point have the same focal lengths. Remember, the focal length is the distance from the focal point to the midpoint of that lens. All right, so there are certain rays that are what we use to draw our ray tracing and our image formation in a convex lens. The first ray is the ray that is parallel to the optical axis. So that ray is going to run from, I'm going to use the top of the arrow as the object location that we are going to be using for light rays in all directions. So we know light's emitting its rays in all directions from the top of that arrow. And one of those rays of light is going to be parallel to the optical axis. A light, as you learned in our description of convex lenses, a light that enters parallel to the optical axis is refracted through the far focal point. So we're going to draw that refraction through the far focal point. All right? Similarly, a ray of light that goes through the near focal point is refracted parallel to the optical axis. Now it turns out that two intersecting lines, that gives us the location where the top of the arrow is going to be represented in the image. But there is one more principal ray, we call these principal rays, that helps us to solidify this location. And that is a ray of light that is in line with the center of the lens, remains unrefracted. So it just travels straight on through, and I have a little bump there in my board. So that was not a very good line. Just kind of erase that a little bit. I'll just redraw that. There we go. A line that is in line with the center of the lens remains unrefracted. So it just draws straight through. So these three rays of light all intersect at one common point. Okay? And that common point represents the top of the arrow. And so we can draw our image here with that top of the arrow represented as the top of the arrow of our object, where all those rays of light cross. Now, I chose the top of the arrow, but if I did the same thing with the middle of the arrow, parallel ray of light would have refracted through the far focal point. Near focal point would have refracted parallel, and a ray of light through the center would have gone through the center and would have been at the middle of where that arrow is, and I could have drawn my image from there. That'd have been a little trickier because, like, how tall do you draw it? But if you are exactly in the middle of this arrow, you'll be exactly in the middle of that image. Okay? We typically use the top of the object. All right, so here's how we draw images in convex lenses, using our ray diagrams. Now, what happens to the image if I change the location of the object? What happens to the image if I change the location of the object? So what I'm going to do is I'm just going to draw another lens right below this one, and I'll draw my optical axis. And I'll draw the same focal points. This is the same lens, it's just another image of it. And I'll draw my arrow exactly the same height in exactly the same location. Now, obviously, I'm not using a ruler, so these are rough exactlies. All right. If instead I were to move my object further away, so I'm going to take the same height object, and I'm just going to move it further away. Okay? So here's my new object location, and I can erase that original object. If I follow the same principle, so practicing, again, our ray tracing, I have a ray of light that's parallel, it will be refracted through the far focal point. A ray of light that goes through the near focal point is refracted out parallel. And a ray of light that goes through the center of the lens remains unrefracted. And I see that my object has done something different. What has it done? It's changed locations, so it has moved closer to the lens. So as my object moves further away, my image moves closer to the lens. And we also notice that it shrunk. As my object moves further away, my image gets smaller. So we can use ray tracing to get a general idea of how moving the object relative to the lens changes the image's size and the image's location. I encourage you to practice what happens if I move my object closer to the focal point. What happens if I move my object closer to the focal point? So practice that one. We're going to actually do one more in this example, and we're going to look at what happens if I move my object inside the focal point. And when I do that, I want to make sure we define one more thing about these lenses. We see that the image that's formed is inverted. And indeed, if I put a screen at this location, I would produce an image on that screen. If I put a screen at this location, I would produce an image on that screen. Because we can produce an image, this image is formed by the true intersecting of lines, we call this a real image. And all inverted images is our clue that we have a real image. The lines, that's real because the light rays are actually intersecting to recreate the object in that image. Okay, so they're actually intersecting. So the question is, what happens if I move my object inside the focal point? And I think I might have enough space, so I'll just lower this. We'll do one more. And I think what I'll do is erase this one, just to give me a little bit of space. I guess I should have erased it to begin with. All right. Okay, I'm going to take my same object, same lens, got to move my focal points down. So here's my focal point, here's my focal point. I'm going to take that same object and I am going to move it inside the focal point. So I'm going to put it right here. So now that object is inside the focal point. The same thing is true regarding how the rays of light behave. So a parallel ray of light is refracted through the far focal point. Now, a ray of light's going to be in line with the near focal point. It's just not towards the lens like it is up here. So there is still a ray of light that goes through the near focal point. And if I were to imagine that ray of light coming up here and hitting the lens, I don't really need that lens extended, but I'll extend it just to show the idea. Then that ray of light is refracted parallel. So these are two different rays of light. One that's going towards the focal point, it doesn't hit the lens at all. But the one that is completely in line with that hits the lens, is refracted parallel. And of course, we do have that third one that goes through, that's terrible drawing, that goes through the center of the lens. All right. Well, these three lines are never going to cross, which means these three lines are never going to be able, I'm not going to be able to put a screen somewhere and see an image formed on that screen. But a type of image is actually produced. Because if my eyeball was over here, if I was looking through this lens at this object over there, so here's where my eye is, these three rays of light are the same rays of light that would hit my eye as if the object were actually this object in space. See, if the lens didn't exist and I was just looking at this object, I'd have a ray of light that went like that and a ray of light that went like, excuse me, and a ray of light that went like that, and it would be forming this object in my visual field. So my brain can't differentiate between these rays of light that don't converge and this ray of light, the rays of light that would come from this object as it goes through my visual system. So the image produced exists in my visual system. And we notice a couple things. First, we notice that that image is upright. Upright images aren't real. I am constructing them in my visual system. We call those virtual. Upright images are virtual. Now, we also notice that this upright image is large. Virtual images for a convex lens are also larger than the object. That's for a convex lens. We'll see if you see that when we do the concave lenses. So we can create two types of images with a convex lens. A inverted image, which is a real image. We can put a screen, we can put some film, we can take a picture. Those size of those images and location relative to the focal point change as we move the object. Turns out, as we moved it further away, it got smaller. As we move it closer, it gets bigger. If we're inside the focal point, we always get a virtual image, and it is always larger than the object. And virtual images, of course, are upright. All right, so that's sort of our conceptual image formation. Practice this, move your object around, practice this ray tracing. And in a subsequent lecture, you can look for it. We'll do the mathematical representation of image formation in convex lenses. All right, good job.